Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we are continuing with integration, looking at some useful techniques for solving the more tricky integration calculations, including partial fractions, substitution, and integration by parts. So if you're ready to learn, then let's get into it. Let's start with partial fractions. If I was to say, how can we integrate 1 over x times x plus 1, you might be a bit puzzled of how to approach this, but partial fractions, in this case, helps quite a bit. We can split up our integrand into two separate fractions and then integrate those separately. So if we do that, we can say 1 over x plus 1 equals a over x plus b over x plus 1. And if we combine these fractions on the right, you can see that it will be a times x plus 1 plus b times x, all divided by x times x plus 1. And so what we can see from here is this numerator of our fraction must equal 1. So I just rub out that. You can say that part must equal 1 because of the left hand side here. And to work this out, we can times our a bracket out and say ax plus a plus bx is 1. The x terms must cancel, and we'll be left with a equaling 1. So a equals 1, and therefore b must be minus 1 to get the ax to be cancelled out. So the x here be x, and this has to be minus x, so b must be minus 1. And if we sub that back in up at the top, it would result in this integral being equal to the integral of what is a, well that's 1 over x, plus what is b, it's minus 1 over x plus 1. And now we can see this is just two separate integrals. We've got the integral of 1 over x dx minus the integral of 1 over x plus 1 dx. Doing this has made it much more simple to work out. This first integral is just equal to log of x, and the second integral is log of x plus 1. And because it's an indefinite integral, we'll just have this constant added at the end. And so if we can then combine these logs, we'll have log of x over x plus 1 plus that constant. Now let's consider substitution, also known as change of variable. So if we start with this first example of the integral of x e to the minus x squared, this will be quite difficult to tackle initially, but if we use substitution, where we say let u, this new variable, equal x squared. Now this isn't just a change of x to u, so it's some sort of change of dummy variable. This is a new variable we're defining as x squared. That will mean that our du equals 2x dx, i.e. we've just differentiated this equation. We can also say that that would be therefore that half du, what is taking the 2 across, is equal to x dx. And so this x dx is that term and that term times together, so we can just replace those two by half du, and we'll have half du. And so this e to the minus x squared is just now e to the minus u. This is a much easier function to integrate. So integrating this is just going to be minus a half e to the minus u plus our integration constant. So now if we undo our substitution, where u is equal to x squared, we're left with minus a half e to the minus x squared plus the integration constant. And you can see how this method has just made that whole process a lot easier to work out. So for trigonometric integrals, we can often try this substitution where I've defined t to equal tan of x over 2. And to see how this is useful, we'll want to start with the double angle formula for sine and cos. So if we look at the first of our double angle formula for sine x, you can see this has just been split into x over 2. So you can imagine this is like 2x, and these would be x for how you'd usually see the double angle formula. And what we can do from here is times everything by 1 by timesing it by cos over cos. So we would have 2 times sine over cos. We can take the denominator of our cos over cos, and will result in tan of x over 2. And then take the numerator, and we'll end up with cos squared of x over 2. Now from here we can divide by 1 by dividing by sine squared plus cos squared of x over 2. And to make things easier, I'm going to use these shorthand. So we'll be using this variable we've defined here, but I'll also use that cos is c and sine is s. I should probably put the c next to where it's just cos instead of cos squared. Therefore, this will be 2 tan times by cos squared over sine squared plus cos squared. And now, if we divide by 1 over cos on the top and bottom, so we'll have times by 1 over c squared over 1 over c squared, would get that this is 2t times 1 over t squared plus 1. Therefore, this is just 2t over 1 plus t squared. That's our simplified way of writing sine x, and you'll see why this is useful later. Here's the double angle formula for cos of x, and if we take a factor of cos squared out from both of these terms, will result in cos squared x over 2 times by 1 minus tan squared. And from here we can do a similar thing that we did before, where this cos squared term will basically turn into this 1 over t squared plus 1. And so we'll be left with 1 minus t squared over 1 plus t squared. So to look at this graphically, we could see that this relationship between sine, cos and our tan of x over 2 can be visualised with this triangle. So having a height of 2t and a length of 1 minus t squared, and then our hypotenuse is 1 plus t squared, forms a right angle triangle, and we can see getting cos x is just going to be our adjacent over our hypotenuse, and then sine x is the opposite over the hypotenuse. And then so tan should be 2t over 1 minus t squared. That should equal tan of x. And if we look at the double angle formula for tan of x, we'd see that it is indeed 2 tan of x over 2, all divided by 1 minus tan squared of x over 2. So looking at it graphically, we can see that our method has been correct so far in determining how we're going to convert from just sines and coses into our variable t. Finally, we might want to know how dx and dt relate. So if we look at dt by dx, this is just our d tan of x over 2 by dx. This will be a half sec squared x over 2. This factor of a half has come from differentiating this a half x in the tan x over 2. From here we can use our trigonometric identities and see that sec squared is the same as 1 plus tan squared. So this is 1 plus tan squared of x over 2 over 2. And so that's the same as dx by dt equaling 2 over 1 plus t squared. Finally, we can use these relations to help us with substitution for an example. So what we're using here are this sin x equaling 2t over 1 plus t squared, this cos x equaling 1 minus t squared over 1 plus t squared, tan x equaling 2t over 1 minus t squared, and our dx by dt to convert what we're integrating over. If we use our example here of 1 over 2 plus cos x dx, so the same as saying the integral of dx by dt times by 1 over 2 plus 1 minus t squared over 1 plus t squared, and that's times by dt. So this dx by dt times dt would give us our dx again, and we've just substituted in our cos x relation. Next, we can substitute in our dx by dt and see that this will be 2 over 1 plus t squared, and also simplify our second fraction. So this will be 1 plus t squared over 3 plus t squared. That's t again, there you go. Integrated over dt, and therefore that's 2 times by the integral of 1 over 3 plus t squared dt, which equals 2 over root 3 arctan of t over root 3 plus c. And now we can substitute in t again, and we'll have our answer of 2 over root 3 arctan of 1 over root 3 tan x over 2 plus c. So for this example, we're integrating between minus 1 and 1 of 1 plus x over 1 minus x, all square rooted. And a good thing to do, strategy in general, is to consider doing something about the square root. In this example, we could substitute in x to equal 1 minus 2u squared, and that will mean that dx equals minus 4u du. And if we're looking at changing the limits as well, we're going to be saying that when x is 1 for the top limit, we're going to have 1 minus 2u squared, which gives us that u equals 0 at the top, and then for minus 1 equals 1 minus 2u squared again, and that time it will result in u equaling 1. And so what we'll have is an integral between 1 and 0 of substituting in 1 plus 1 minus 2u squared over just 2u squared, as the ones will cancel, all square rooted, times by our minus 4u du. And what we can do is use this minus sign here to flip the limits of our integration. So the minus sign we can get rid of and result in 0 to 1. So we can put the u from the outside into the bracket, and that will result in it being a u squared now, as it's in a square root. And so we'll have the integral from 0 to 1 of, and all these, this will become a 2, and all these 2's can cancel out, and we'll be left with 1 minus u squared, and then times by u squared from the outside, all divided by u squared. And obviously these u squareds cancel, and that's still square rooted, times by 4 du. Therefore we have 4 times by the integral of 0 to 1 of 1 minus u squared, all square rooted, du. From here, we might want to say let u equal sine theta. Therefore du equals cos theta d theta. And if we substitute that in, we'll have that 4, and now the limits, when u is 0, we'll have that theta must also be 0 for sine theta to equal 0. Then when u is 1, we'll have that theta is pi over 2. And now the integrand is going to be 1 minus sine squared square rooted, so that's the same as cos squared square rooted, so we'll just have cos theta times by our cos theta d theta, which is just 4 times by 0 pi over 2 of cos squared theta d theta. And our cos squared, from a double angle formula of cos 2 theta, is just 1 plus cos 2 theta all divided by 2 d theta. And so we're left with 2, because this, we can take this half out and it'll become 2 on the outside, so it's just 1 plus cos 2 theta, 2 times theta plus a half of sine 2 theta between pi over 2 and 0, and this just results in pi. So our final substitution example, I think, is quite clever. if we have our integral I equaling the integral from 0 to pi over 2 of sine squared theta d theta, and our substitution is to let this new variable phi equal pi over 2 minus theta. So that will mean that d phi equals minus d theta. And to change our limits, when theta is pi over 2, we're going to have phi equaling 0 on top. And then on the bottom, we'll have theta equaling 0 is going to be therefore that phi is pi over 2. We can rewrite this integral as the integral from pi over 2 to 0 of cos squared phi times minus d phi. And if we just again use this minus sign to flip the limits, we can write that we have the integral from 0 to pi over 2 of cos squared theta d theta. Now if we just change the name of our dummy variable phi to now be theta again, this isn't doing any mathematical substitution, it's just changing the name of our variable. You can see that this is going to be cos squared theta d theta. And what you can do from here is see that if we just add this integral here and this integral together, they're both equal to I, so we can say that 2i equals integral from 0 to pi over 2 of sine squared and also of cos squared, so 0 to pi over 2 of sine squared theta plus cos squared theta d theta. And we know that sine squared plus cos squared is 1, so that's just the integral from 0 to pi over 2 of 1 d theta. And that is simply just pi over 2. So therefore I is pi over 4. And I just think it's quite a clever method to work this out, and you can use this substitution where you've got a change of pi over 2 to change between cos and sine, and it's quite a satisfying method. You'll see that crop up. Our final method for solving some more tricky integration problems is integration by parts. So if we use the product rule of differentiation, it can be shown that the integral of u dv by dx equals u times v minus the integral of v du by dx. And this is sometimes written as the integral of uv prime dx equals uv minus the integral of v u prime dx. And see an earlier video for what the product rule of differentiation is, but you can try and work out how this formula comes about, and this is our main formula for integration by parts. For our first example, we have the integral of x e to the x dx, and here we can say that x is our u and ex is our v prime from this equation above. And so all we're going to have is u of v, so what is the integral of v prime? Well, that's going to be e to the x still, so it's just going to be x e to the x. And then what's our u prime? Well, it's just going to be dx by dx, so that's going to be 1. And so we're left with minus the integral of 1 times e to the x, which is just e to the x dx, and that results in x minus 1 e to the x plus c. So you can see this integration by parts, so using this formula above has helped us come to this final answer. Just to write it concretely, you might want to know that u prime is 1 and v is e to the x. And now for our next example, we're going to have the integral of log of x dx. And here we are going to use the dv by dx, so our v prime is actually this invisible 1 that we're timesing everything by, so it's going to be 1 times, but imagine that's inside the integral. So we have v prime is equal to 1 and u equal to the ln x. So v, if v prime is 1, v is x, and then u prime is just equal to 1 over x. Therefore we have uv, so it's going to be x ln x minus the integral of x times 1 over x dx, which is just x. So we're going to have x times y ln x minus 1 plus our integration constant. Today, we've looked at some useful techniques for solving the more tricky integration problems. In the next video, we'll be looking at how integration applies to mean value, area, and length, and this will be the first of 3 videos discovering how integration can be applied. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.